How do coronal mass ejections create the Aurora Borealis? Imagine a giant burst of energy from the sun sending billions of tons of charged particles hurtling through space toward Earth. That's what a coronal mass ejection, or CME, is. These are huge eruptions from the sun's outer atmosphere, called the corona, releasing plasma and magnetic fields into space. When a CME travels through space and reaches our planet, it interacts with Earth's magnetic shield, known as the magnetosphere. This interaction is what sparks the beautiful light displays we see as the Aurora Borealis. The process starts when the CME, carrying electrons and protons, arrives at Earth. If the magnetic field embedded in the CME points in the opposite direction of Earth's magnetic field, what scientists call southward, it allows energy to transfer more easily into our planet's magnetic bubble. This process is called magnetic reconnection. It's like the magnetic fields snap and reconnect, releasing a burst of energy. This energy disturbs the magnetosphere and causes geomagnetic storms. During these storms, the solar wind and CME accelerate electrons inside Earth's magnetic field, especially in the magnetotail, which is the part of the magnetosphere stretched away from the sun. These electrons then travel along Earth's magnetic field lines toward the polar regions. When they reach the upper atmosphere, they collide with atoms and molecules like oxygen and nitrogen. These collisions transfer energy to these atmospheric particles, exciting them. As the excited atoms and molecules return to their normal state, they emit light. This is what creates the shimmering curtains of green, red, purple, and blue that make up the Aurora Borealis. The color depends on the type of gas and the altitude of the collision. Oxygen at higher altitudes produces red lights, while at lower altitudes it creates green. Nitrogen contributes to purples and blues. In Scandinavia and other northern regions, these lights are most vivid because they lie within the auroral oval, the zone where the auroras are most common. Stronger CME events, especially during the peak of the solar cycle, produce brighter and more widespread auroras. Faster CMEs with magnetic fields pointing south tend to cause more intense geomagnetic storms, making the lights more spectacular and visible further south. So, in simple terms, coronal mass ejections send a burst of charged particles and magnetic energy toward Earth. When these particles reach our planet, they energize electrons in the magnetosphere. These electrons then collide with gases in the atmosphere near the poles, producing the stunning displays of the Aurora Borealis we love to watch.